Hello students, I am CG Joy, mathematics teacher, Palloti School, Thrissur. Today I will be continuing Chapter 10 circles. My concentration is on two theorems. Theorem number 1, tangent at any point of a circle is perpendicular to the radius through point of contact. Theorem number 2, the length of tangents drawn to a circle from an external point are equal.
In this video, we are going to discuss about two theorems, okay, and the first theorem is very important. So many times this question asked for the board examination, okay, for 2 marks. Very simple theorem, okay, and this statement is the tangent at any point of a circle is perpendicular to the radius through point of contact. Okay, so tangent at any point of a circle. Okay, so I have marked a point P on this circle with the center O. Okay, so and the point of contact is P. Understood? That is common between the circle and the tangent. Okay, so the tangent at any point to a circle is perpendicular to the radius. Radius means the line segment joining center to any point on the circle, and here that point is point of contact, that is P. That is, we have to show that this OP is perpendicular to the tangent. Okay, so what we have to prove? Okay, so what we have given, okay, for proving a theorem, children, this is the method should be followed. Okay, that is, first you have to write given. Okay, then construction. If we need any construction, that should be written as a second subdivision. Okay, so given construction, okay, then proof. Okay, so and also figure in the right side. So we already have drawn the figure according to the theorem. Okay, so what is given? We have given a circle with the center O and a tangent AB at the point of contact P. Okay, that is given. And what we have to prove? We have to prove that OP perpendicular to AB. Okay, tangent at any point of a circle is perpendicular to the radius through point of contact. Okay, so this is what we have to prove. And for that, what is the construction? Okay, so this comes, so this is to prove, okay, then construction. So construction means which leads to get the result. Okay, for that I have taken a point, okay, Q on this tangent AB other than P. We have already point of contact P. Other than P means along this tangent AB another point Q, and I am joining this OQ such a way that this OQ intersects the circle at R. Okay, so what is the construction? Okay, take a point Q on the tangent AB and join OQ. Join OQ. Okay, now we are going to start its proof. So from the figure, OP equal to OR. Can we write like this? OP equal to OR. P and R are on the circles, on the circle, and they are joined and centered to that point, and that is radius. What is the reason? OP equal to OR? Because radii of the same circle. The same circle. So they are equal. Okay, and see from the figure, can you say that OP is less than OQ? OP is less than OQ? Yes. Why? Because here OQ is the sum of OR plus RQ. Okay, that means, which implies OQ equal to OR is nothing but OP plus RQ. Okay, so you are adding another quantity to OP and that will give you OQ. So OP is less than OQ. Isn't it? That point is clear? Or OQ is greater than OP. Understood? Because OQ is the sum of OR. So this portion is added to OP. Or OP is less than OQ. OP is less than OQ. This will happen, okay, any other points, not only for Q. If you are selecting another point here, S, if you join O to S, this OS intersect the circle at what is it, C. Okay, so OC is the radii of the circle. So this CS is the portion, extra portion. That means OP is less than OS. Okay, except for this point P. You can take any other point, and if you join that point with the center, you can see that OP is always the shortest distance from the point O to any point on the tangent AB. And I have told in the first video of this lesson, the previous video, the shortest distance is always perpendicular. Okay, the actual distance between a point to a line is the shortest distance, and that shortest distance is always perpendicular. Okay, and how we have shown that OP shortest? By taking different points on the line AB. Okay, for all such all points other than P also a point on the tangent AB. Other than P, this will happen for any other points joining center to that point. A small portion is added. Okay, is more than OP. Okay, so OP is the shortest distance and that will be perpendicular. Okay, so how can we write the proof? Okay, among all the points on this tangent AB, OP is the shortest and shortest distance is perpendicular. Okay, which implies OP is perpendicular to AB. Hence the proof. Is it clear, children? This is all about the first theorem. This theorem is also called radius tangent theorem. Okay, that means the tangent at any point of a circle is perpendicular to the radius through point of contact. Okay, yes children, now we are going to prove the second theorem. And what is the statement of the second theorem? That is, the length of tangents drawn from the external point to a circle are equal. Okay, length of tangents drawn from the external point. This situation we have discussed in the previous video. When we have a point, you can locate the point in 3 of the positions in a plane, and this comes for the third case. Okay, now I am marking a point P which is lying outside the circle. Okay, so the length of tangent, how many tangents can be drawn? 2 tangents. Okay, and here the tangents are PA and PB. Length of tangents drawn from the external point to a circle are equal. So what we have to prove? PA equal to PB. Okay, so as I told in the first theorem, we have to follow a format. First we have to write down the given, then prove, construction, then proof. Okay, and figure should come in the right side of the book, okay, or the booklet for the examination point of view. Okay, so given, what is given? A circle with the center O and an external point P. Understood? And what we have to prove? Okay, we have to prove that those tangents are equal, that is PA equal to PB. And in the previous video I told what is length of tangent is the length of the line segment from the point on the circle to the external point, that is PA. Here that is PA and the second tangent is PB, and these two tangents what we are going to show that they are equal. Okay, and for that what is the construction? So construction, Okay, in construction you have to join OA, OB and OP. Understood? So, join OA, OB and OP. Okay, so these are the three very important areas to be concentrated. Including the figure, you can easily score half of the mark. Usually this question comes under section C for 3 marks. So you will get 1.5 mark for writing up to this. Okay, and in the fourth case, that is the content of the theorem, that is proof. You have to consider, you can see two triangles. Okay, one is above OP and another one is below OP. Okay, so OAP and OBP. Okay, so consider triangle OAP and triangle OBP. Isn't it? Okay, and we are going to show that they are congruent. By theorem number 1, tangent at any point of a circle is perpendicular to the radius. Okay, so here the point of contact is A. So OA perpendicular to PA. The same way OB. Okay, radius tangent theorem. Okay, the line segment joining center to the point of contact. Here that is OB. There it is OA. Okay, so you can write, okay, because of the theorem number 1, don't write theorem number 1 for the examination. So since the tangent at any point of a circle is perpendicular to the radius, we have OA perpendicular to PA and OB perpendicular to PB. I hope this step is clear. Okay, because of radius tangent theorem. Okay, since it is both are perpendicular, can you write or can you mark this is 90 degree and this angle also 90 degree. So with respect to triangle OAP, angle OAP, A should come in the middle, okay, equal to angle OBP equal to 90 degree. Understood? Because we have already mentioned the reason, okay, because of this radius tangent theorem. And we have to write 3 reasons, then only you can easily reach into any one of the criteria, congruence criteria. So for that we have now one step, that is angle OAP equal to angle OBP equal to 90 degree. And what else? Okay, so in triangle OAP, OA, the side OA, and in the second triangle OBP, the side OB, both are equal because both are the radii of the same circle. So this is the second step. OA equal to OB, radii of the same circle. The same circle. Okay. And the third case, that is OP is one of the side and the same side OP comes in the second triangle OBP. So OP is common. OP equal to OP, common side, implies, what is that? Triangle OAP is congruent to triangle OBP. Which criteria? Okay, SSS, SAS, RHS, so many criteria we already learned in 9th standard. Here which criteria? First of all, it is 90 degree. You can think of RHS criteria in a right triangle. Okay, one side and hypotenuse. Okay, is respectively equal to one side and hypotenuse of the another triangle. So those two triangles are congruent. So by RHS criteria, okay, you can write the reason as RHS congruence criteria. Okay, so we have got these two triangles are congruent, which means what we need to prove? PA equal to PB. PA and PB. PA is second and third. that is the line segment join. Here the second and third, the line segment PA equal to PB by CPCT, corresponding parts of congruent triangles. Okay, that means this is the required result. We have reached what we need to prove is the length of tangent drawn from an external point to a circle are equal. Now we have seen that length of tangents drawn from an external point to a circle are equal. Okay, by joining OA, OB, OP, by considering two triangles, we have shown that they are congruent. From this very important symbolic form, you will reach into another important result. That is, I will write what we have shown, how we have proved this PA equal to PB by proving triangle OAP is congruent to triangle OBP. Okay, in theorem number 2, since we need PA equal to PB, we have taken PA and PB and they are equal because CPCT. Okay, and in the result is this. These tangents are equally inclined at the center. Tangents PA and PB equally inclined. Okay, that means these two angles are equal. Understood? That means in triangle OAP, angle O equal to angle O of triangle OBP. So, this is the angle, okay, at the center. Okay, very easily you can show that. So, first of all, you prove this one. Okay, if that result is asked in terms of theorem, you prove that they are congruent, that is prove this. Okay, that is triangle OAP congruent to triangle OBP. Okay, and what we need? Angle O, that is angle O of triangle OAP can be written as, which implies angle AOP equal to angle BOP. What is the reason? CPCT. CPCT. See the position, first position and first position. So, you can keep that vertex as the middle, so that you can easily get, you can easily represent that in terms of three vertex, that is AOP. For the second triangle, BOP. And the very important second result is, these tangents are equally inclined at the line segment joining center to the external point. Which is the line segment joining center to external point? OP. Understood? So, this tangent PA and PB are equally inclined. So, that means the angle between OP and PA. Okay, PA is length of tangent and OP is the line segment joining center to the external point. Okay, and that angle is from the figure angle APO. Will you get this result from this congruence symbolic form criteria? RHS criteria, that is angle AOP, and what is the angle between this tangent PB and the line segment joining center to external point? That is this angle, that is angle OPB or BPO. That particular point should come in the middle. Okay, that means angle BPO. This is again by CPCT. I will show you, children. This required angle is P on both the triangles. P is in the third position, here also third position in the symbolic form. That means that corresponding angles are equal. Here angle P corresponds to angle P of the second triangle. Okay, so these are the very important results you can easily get by proving the length of tangents from the external point to a circle are equal. Okay, so all these three results, first we have to show that triangle OAP is congruent to triangle OBP. Okay, and by applying CPCT, what all result needed, you can easily reach into that result. This is all about the theory parts of this very important lesson, circles. Okay, and in the next video we will solve the exercise problems from this lesson. Okay, thank you for watching and supporting me. Thank you all.